This is our AP Statistics project by Anna, Freja, and Adia. Have you ever wondered how much appearance really matters and whether guys and girls see it the same way? For our 2025 AP Statistics project, we explored that same exact question by researching gender-based differences in beauty standards. We asked ourselves, is there a statistically significant difference between boys and girls in how critical they are regarding physical attractiveness at Granada High School? Through this project, we hope to gain insights that could help promote healthier and more thoughtful attitudes towards attractiveness, rather than solely focusing on surface-level appearance. For this study, we used a multi-step clustered random sampling method to ensure that our sample represents Granada's diverse student body. First, we compiled a complete list of all the classrooms at Granada. Each classroom was treated as a cluster. We numbered the classrooms from 1 to 103 and used the TI-84 calculator's randint function to randomly select 20 classrooms from this list. For example, we typed randint 1, 103, 20 to generate a list of 20 distinct classrooms. This ensured that every classroom had an equal chance of being selected, reducing selection bias. Additionally, each teacher at Granada typically teaches 6 periods a day. Once a classroom was selected, we used randint 1, 6 again to randomly choose one of the teacher's 6 periods. If the selected teacher does not teach during the chosen period, we select the next available period chronologically. For example, if we selected Mr. Clifton's classroom and randint function returned 5, we need to account that Mr. Clifton does not teach during 5th period, so we would default to his 6th period class to obtain data from. This ensured that the period selection remained random, but still allowed for a valid sample. Finally, we distributed surveys to every student present in the randomly selected class period of each chosen teacher. The samples are independent because students were randomly selected from different classrooms and periods across campus, with no student appearing in both groups. By the end of the sampling process, we stratified it by gender to create 2 independent samples, N1, which had 45 boys, and N2, which had 31 girls. Each group exceeded 30 students, so according to CLT, we can say that the sampling distribution is approximately normal. Ultimately, this sampling method is effective because it ensures fairness in selection, minimizes potential bias through randomization, and ensures that the samples are balanced and comparable for statistically analyzing the data.
This was an observational study because we simply observed and recorded how students rated the attractiveness of individuals in photographs without manipulating any conditions. We did not assign any treatments or alter the setting in which ratings were given. Each student completed a Google Forms survey that included a set of 10 pictures, 5 male and 5 female faces in alternating order in order to maintain balance and reduce potential gender ordering effects. These pictures were selected to ensure a diverse range of physical features such as race, hair length, and eye color. Each image was also labeled with the letter A through J, and students were asked to rate each individual's attractiveness on a scale from 1 to 10 based on their own perception. The first page of the Google form asked students their grade level and to select their gender that they best identified with, and the given options were male, female, and prefer not to say. We could then break down responses by demographic groups and analyze whether patterns in attractiveness ratings differ by gender or by grade. We included the prefer not to say option in order to promote comfort and reduce potential response bias, especially since gender identity might influence how students perceive or rate physical attractiveness. By placing these demographic questions at the beginning of the survey before any image evaluation, we avoided influencing how students might rate based on who they assumed that the survey was targeted for. To reduce response bias, all students completed the Google form individually, anonymously, and we ensured that the survey responses were not influenced by peers or by teachers. We only collected grade level and gender to preserve the anonymity of all participants. Female respondents, represented in pink, gave higher average ratings than male respondents, represented in blue. The mean of females was approximately 6.9 compared to 5.8 for males. This indicates that females evaluated more positively than males. When examining the frequency of each rating, the distribution for females showed a clear skew toward higher ratings, with the most common responses being 8 and 9. This suggested that female respondents generally rated items more favorably and consistently within the upper range of the scale. In contrast, the distribution for males revealed a more polarized pattern. While many males also gave high ratings, particularly between 7 and 10, there was a sharp spike at rating 1, which was not present in the female distribution. In summary, female responses were more positively skewed and consistent, while male responses were more varied with both high ratings and a notable concentration of very, very low scores. These differences in response patterns contribute to the observed gaps in mean ratings between the two genders.
For our confidence interval, we will be conducting a 2-sample T interval to estimate the difference in mean attractiveness ratings between boys and girls. This method is appropriate because we are taking 2 independent random samples, one for boys and one for girls, and we are comparing their mean ratings on a numerical scale. We will use a 95% confidence level, which means that if we were to repeat the sampling process many times with samples of a similar size, approximately 95% of the calculated confidence intervals would contain the true difference in population means. As for interpreting the confidence interval, if the confidence interval includes the value of 0, it suggests that there is no significant difference in how critically boys and girls rate attractiveness. If the confidence interval is entirely below 0, it suggests that boys tend to be more critical in their ratings than girls, but if the confidence interval is entirely above 0, it suggests that girls tend to rate attractiveness more critically than boys. By computing this interval, we will be able to gain insight into the magnitude and direction of the difference between boys' and girls' judgment of attractiveness, helping us ultimately decide whether or not gender plays a role in how critical students are rating physical attractiveness. Now, after all of the calculations are said and done, the confidence interval is entirely negative. It does not include 0, so we can conclude with a 95% confidence that the mean rating given by females in a similar population is significantly higher than that given by males. This suggests a meaningful difference in ratings between the two groups, with females tending to rate higher on average. And we also conducted a chi-square test for homogeneity. We chose this statistical test because it is appropriate when comparing the distribution of categorical responses across 2 or more populations. In this case, the boys and girls of Granada High School. We are evaluating whether distribution of attractiveness ratings, 1 through 10, is the same across gender groups. Our null hypothesis is that the distribution of attractiveness ratings is the same for boys and girls. In other words, gender does not affect how students rate physical attractiveness, using a significance level of 0.05. Our alternative hypothesis is that the distribution of attractiveness ratings is different for boys and girls, and that gender does influence how students rate physical attractiveness. This is a chi-square test for homogeneity, not independence, because we are comparing 2 known groups, boys and girls, and 1 categorical variable, their attractiveness rating. And our calculations concluded that the observed ratings between males and females are significantly different, so we reject the null hypothesis because our p-value is super duper tiny. It's far below 0.05. There is strong evidence that the gender and rating distribution are not independent.
One significant challenge was the presence of outlier responses, such as participants who consistently selected the lowest rating, all 1s, or the highest rating, all 10s. With these responses, it was hard to tell if their ratings were genuine or if they were giving the same ratings to all pictures just for fun. These outliers had the potential to skew the results and required us to be a lot more cautious while producing and interpreting our results. Additionally, there was an imbalance in gender representation with more male respondents than female respondents. A large number of students also did not respond to the survey at all, and in many cases, teachers did not distribute the survey to their assigned class period. This led to a significant non-response bias, and it reduced the size and balance of our overall sample, which may have affected the distribution and reliability of the data.
Indicated to us that gender and attractiveness ratings are not independent variables. This means that the distribution of ratings differs significantly between male and female respondents, suggesting that gender influences how individuals perceive and evaluate attractiveness. The confidence interval analysis further revealed that the mean rating given by females, 6.86, is consistently higher than that given by males, 5.8. This substantial difference indicates that women tend to rate attractiveness much more generously or positively compared to men. From these findings, we learned that perceived attractiveness is experienced differently between males and females, introducing valuable insight into social interactions, relationship dynamics, or even industries such as advertising that heavily rely on perceived attractiveness. This information is helpful because it reveals the presence of bias in situations where we might expect objectivity. In areas like dating apps, advertising, or even academic research, understanding how gender influences perception can lead to a more accurate interpretation of data. It also encourages us to question the neutrality of subjective evaluations and to consider the underlying factors that may shape them.
While our study does not tell us why these differences exist, that would be an interesting query to explore further on. If we were to do this study again, there are several different ways we can improve it. Increasing the sample size would help make our results more reliable and reduce random variation. We could also include a more diverse group of participants in terms of age, cultural background, and sexual orientation, because these factors could influence how people rate attractiveness. Controlling for variables like mood, fatigue, or prior experience with similar studies would also help us isolate the effect of gender more clearly. Additionally, making sure participants are blind to the study's purpose would also reduce the risk of biased responses. To expand the study and apply it to a larger population, we would need to recruit participants from different regions or countries and include more gender diversity beyond just male and female categories. This would help us understand whether the observed trends hold across cultures and identities and make our findings more inclusive and generalizable.